Hello, and welcome to our program, Astronomy for Everyone. We're here today in Adrian, Michigan, the facility of PlaneWave Instruments. With me to talk about what they do here is, first off, the CEO of the company, Rick Hedrick. Rick, welcome to the show.
Thank you very much. It's great having you guys here. We're going to go into building 45 here shortly, and we'll see where we assemble our larger telescopes, our 0.7 meters and 1 meters, and also where we assemble our optical tubes of all the sizes that we make. And there's also some testing equipment in there. It's a neat building. It's where a lot of the action is. And this is Ralph Emerson, our VP of Marketing and Sales, and he'll talk a little bit about Building 44 next to us.
Yes, thanks, Rick. We're going to go take a look at Building 44. In that building, we are assembling some of our newest products, and I think everyone will enjoy seeing that.
All right, thank you, gentlemen. Let's head inside and take a look. Hi, we're here inside the CDK Cassegrain Assembly Building here at PlaneWave. And to tell us all about what we're going to see is the CEO, Rick Hedrick. Rick?
Thanks. Right now we're standing in front of a 24-inch telescope being assembled. This is the primary mirror. It's and it's been mounted into the back plate. And the rest of the telescope still needs to be assembled, but you're seeing it in a nice state here. So it's 24 inches, a 0.6 meter, and as you said, the type of telescope we normally make here is a CDK, which is a corrected Dow-Kirkham. Here are other primary mirrors that have been mounted, but not yet mounted in the back plates. Or here's a couple that are actually smaller ones. These are 12.5s mounted in back plates, and here are two 14-inch mirrors, just mounted on their cell, not yet mounted in the back plate. And then back over here in the background, we've got optical tubes. You see 12.5-inch, the long carbon fiber tubes up there. Those are for our 12.5-inch telescopes. And we have a lot of the inventory for the optical tubes back in this area. Right here, we're looking at a front ring to a 1 meter telescope. This is where a secondary mirror would be mounted. And this is where the primary mirror would be mounted for a 1 meter telescope. So this is the back plate of that system. And over here we have this is the top cage for a 0.7 meter or the CDK 700 telescope. We'll see more of them coming up. Secondary mirror would mount here. And this is just waiting for the rest of the assembly.
Well, that's very interesting, Rick. You mentioned some other objects or items a little bit farther back here in the assembly building, so let's head back and take a look at them.
Sounds good.
Rick, can you tell our viewers about the construction here of some of these CDK 700 telescopes?
Sure, yeah. So what we have here, as you said, is the CDK 700. So it's a 0.7 meter alt-azimuth telescope. It has dual azimuth focus, which means the focus of the telescope comes out here. Light comes in the top, hits a primary mirror, goes up, hits a secondary, hits a tertiary mirror, and comes out the side. And this tertiary mirror, or M3 mirror, can rotate and also send the light out the other side of the telescope. So you can have a camera here and, say, an eyepiece over there, or a spectrograph and a camera, Also, it's a direct drive mount, so there's no gears. And we'll look closer at some motors later, but we make the motors here also. So this is direct drive. It's dual azimuth focus, 0.7 meter. Here's another one in a different state of being assembled. Doesn't have the top cage put on yet, but we can see this in this state. And then over here we have a motor for a 700. It's a motor and the main bearing. You can see this thing moving here. See, this is what goes inside right over here. So this is sitting on top of this motor. And this fork back here actually sits on top of this. So that's how you start to, that's how this starts to build up into this telescope. So in addition, you can see that in the background now we have a 1 meter fork being built. So that's the kind of the next section for us to look at.
Interesting. Let's head back and take a look at that.
Sounds good. Okay, we're here now with the 1 meter telescope, and like the CDK 700 we were talking about before, this is a direct drive motor, so there's no gears, I can just move it around up and down. It's right now this particular one has the primary mirror in it and the M3 mirror in it, which is the tertiary back here. It's waiting for the secondary mirror here to come back from coating, so it is not balanced. It wants to go right about here. But here we can look at the telescope, and as we were talking about before, you have an M3 here. This M3 can rotate. So right now it's set to send the light out this Naismith port. Each one of these is a Naismith port here. So if we rotate this mirror around, we can send the light out this Naismith port, and you can have a camera here or a spectrograph. You could have another piece of equipment on the other side. A lot of people use these telescopes remotely, and they'll switch from one camera to another or one instrument, etc. You can also look, let me point it up here. So here we see the profile of the primary mirror. Now this is a light-weighted 1 meter mirror made of fused silica. The first thing we designed when we designed this telescope was the mirror. Actually, the whole key to the design was the mirror. We wanted to make a lightweight telescope for a 1 meter. This 1 meter telescope weighs 3,500 pounds. Most of the time they can weigh 10,000 pounds. And it all starts with the mirror. It's how do you support the mirror. So this is a 120-pound mirror, and that means the whole telescope can be a lot lighter. So we actually, behind here, there's light weighting holes, it's the whole key to what we've done with this telescope is started off with that lightweighted mirror. And what it means is the mirror can cool faster. The mass of the telescope is less, and the blank that we're buying now is thinner. So we're not paying as much for the expensive material that the mirror is made of because we can buy a thinner piece. So it brings the price down. It brings the weight down. We can install one of these in 1 day because everything is much lighter weight. Some other things to look at here. Let me rotate it here. Here we have the drive electronics down in here. We actually have them on both sides. So these are the drives that drive the motors. One's the azimuth motor, which is this axis, and the altitude motor, which is this axis. And so that accounts for 2 of the drives. But there's also 2 more drives on the other side, and they drive a derotator. So this is also a direct drive motor that derotates your image. So on an Altaz telescope, the stars come up this way, and they rotate in your field as you're tracking the stars. So this will keep your camera oriented such that the stars won't rotate. It's called a derotator. There's also drives for the focusers. So there's a lot of electronics that ends up going into these telescopes. And speaking of drives, we can come over here. And here we can look at the motor inside of another 1 meter telescope. This one's not as assembled yet, doesn't have optics in it, but the motor is uncovered, and you can see the coils and the magnets. And in the building next door, which we'll go to after this, is you can see where we wind the coils and build up the motors. We make a lot of different direct drive motors now, and the first step in those is winding a whole bunch of coils. And now in the background here, we have another 1 meter that is it's actually a completed 1 meter. And where it is, it's in our test tower. So this is where we optically test a finished telescope. And up above, we have a 1 meter flat. And that's an optical flat. And it's very few companies are able to do this, are able to test full aperture finished telescopes. So the steps that we do in testing telescopes here at PlaneWave is we test a primary mirror. We make a primary mirror in yet another building. And we make the primary mirrors, and we test them, and we get them to, better than diffraction limited, usually 0.93 Strel, 0.94 Strel. And then you take the mirror, you have it coated, and you bring it back, and you mount the mirror. And this is where a lot of bad things happen with telescopes, is you mount the mirror, and that's when you mess it up. It's not that hard if you have good metrology to make a good mirror. What's hard is to mount the mirror and not mess it up. And most people don't even measure that. A lot of companies will tell you, they'll just give you the tested primary mirror, and they'll say that's what their optics are. And it's true that they may have made the optics to that quality, but they didn't mount it. So then you mount the mirror, and we test it again and make sure we didn't change it. And we've gone through great engineering struggles and designs over and over to get a mirror cell that holds our mirrors without changing their shape. And then you take the whole system and you put it together. We test we make our secondary mirrors. We do similar tests on those, test them after they're mounted. You put the whole system together, and then you want to test the complete system. So if there's any residual errors, you can fix them. What we do is we take, so in this test tower back here, if there's any residual errors in the complete 1 meter or 700 or 24, any of the telescopes are being tested, we take off the secondary and we hand touch up the secondary to fix any residual errors. And that way we get a complete diffraction limited finished product. And very few people are actually testing the complete system. They give you their individual, optics being tested. So we do this all the way down to our 12.5. We don't do the 12.5s in this big test tunnel. We have another test tunnel that's smaller for testing 20-inch telescopes and down. So that's kind of it for this building.
Well, thank you, Rook. It's been an amazing tour in Building 44, the assembly and test building. And next, we're going to head next door to check out how they wind some of the motors for these telescopes and also the LMount assembly. So we're going to take a quick break right here. If you have a question, please send us an email. You can see the address down there at the bottom of your screen. Coming up next is Term of the Month. Stephen?
Thanks, Don. The term of the month is Comet Borisov. So, Comet Borisov was discovered recently screaming into the solar system from outer space. And we have a picture of it. It's right there in the center. All of the stars are long lines because the comet itself is what the camera was tracking. And so you have the nucleus of the comet with the tail going up and to the left. So this was taken with a 17-inch PlaneWave telescope, and it is owned and operated by the Virtual Telescope Project. This is an organization where you can essentially buy time on the telescope, and you can be sitting at your desk, at your computer, and get the images and see what's going on. And the telescopes, and you can be anywhere on the internet, and the telescopes are wherever they are. So that is the term of the month, Comet Borisov.
Thanks, Stephen. I'm here inside Building 44 at PlaneWave Instruments. I'm standing next to Ralph Emerson, the Vice President of Marketing, who's going to go over some of the equipment that we can see here. Ralph?
Thank you very much, Don. Well, as Rick said, our company is known for our superlative telescopes, but now we're also known for our mounts. This is our new LMount series. This telescope mount is a fork mount. This is an alt-azimuth mode, as you see here. We're utilizing the drive system that we developed for our larger telescopes. This is direct drive. It has no moving parts inside, so there's no gears, which means that you don't have backlash, you don't have periodic error. We also, this mount comes with great encoders, so the pointing accuracy is fantastic. We're going to move over and take a look at another version of the mount.
Okay, let's head over here in just a second. We'll take a look at it.
Okay, now we see our equatorial configuration of the LMount. This is the L600 and we have a 600 millimeter telescope here. And you can see that the wedge at the bottom is angling the telescope for a given latitude. This mode is generally used for photography, for imaging. This allows for less movement of the camera, and it gives you superlative results. Don, as you saw downstairs with our telescopes, we virtually make everything for our equipment. And since our mounts depend on the direct drive motors, we actually build our own motors rather than buying some commercially available motor that might not be up to par for astronomy. So what you're looking at here is the coiling process and the buildup of the actual motor. And now you see a continuation of the buildup of the motor, the coiling process. Once it's hand coiled, then the actual leads are fed through a metal ring, and then that moves on to the actual assembly of the actual physical motor itself. And now you see here we bring these coils together and we fit them, and now you see basically a magnetic ring. These rings are combined to form a magnetic field that separates the rings and allows for the motor to move progressively in a circle. And over here you see the assembly of the housing, the primary housing for the motor. And then once that has assembled, we come over here and the rings and the housings go together, they're fitted together and then tested. And once that is done, we have a completed motor assembly here, direct drive motor. Okay, down here you'll see that we have a number of our mounts that have come over from our assembly and manufacturing areas. These are the larger mounts. These are the L600 mounts here. They're waiting to get their motors and other parts inserted. Here you'll see the wedges that are being made. These, by the way, are fabricated to the actual latitude of the observatory. And then below here there are additional base plates for the direct drive motors. Okay, down here you'll see several of our L350s. These are the smallest mounts that we make currently in the L series. But most important thing I wanted to show here is that, you know, for most astronomers, you're familiar with the dovetail and saddle plate configurations that generally you use with most mounts to hold a telescope. We utilize the same system here. So this happens to be one of our mounts, saddle plates, but you could use a Losmandy or other saddle plate here to hold your OTA onto the mount. This is, as I said, the most popular because it's a little smaller and a little bit more affordable. And for most people, it'll accommodate up to like about a 14-inch telescope. Don, what you see here is an example of our company's utilization of the highest technologies that we can afford in manufacturing. Gives us a higher quality product. This is a 3D printer. It's being used to manufacture part of the baffling that's used in our larger telescopes. These are parts that are extremely difficult to make any other way. And the materials that are used are difficult to use as well. So as a consequence, we're utilizing 3D printing and other high-tech manufacturing processes.
Ralph, this has been a fascinating look at how you design and build the components for your telescopes. Now, we're down here looking at an almost completed L600. If you could talk a bit about how this is finished out.
Yes, thank you, Don. Well, what you'll see here is an example of the L600. The L600, as well as the other telescope mounts that we make, are designed to be used in robotic locations. So one of the features of the mount is the cable management system. The cable management system allows you to route the cabling of the any other components that you might have, such as cameras or spectrographs or other instruments. The cabling can be mounted through the housing of the telescope mount itself, so that you don't have to worry about any entanglements when you are operating the telescope. Also, additionally, we have other areas that we designed so that you can put other instrumentation and other equipment located inside of the internal parts of the mount. Again, so that you can operate this without fear of entanglement or other matters. The mount itself is professional grade. So you can do real research with this mount. If you're an astronomer, an amateur astronomer, you can do great photography with this mount. We have other people that are looking at the mount for things like satellite tracking and other applications for this mount. So the complete system itself, you can use different OTAs. Here you see a 20-inch OTA on this L600, but as we saw earlier, you can go up to as large as a 24-inch or 600-millimeter telescope here.
I'm noticing that this is set on its skid and ready to go, and looking down at the bottom, what would the end user typically mount this scope to?
Well, all our mounts are designed to be used in observatories. So typically you would have a pad and a pier, a concrete pier poured. Then you might have a smaller metal, short metal pier, and this telescope mount would then fit to that pier. And but it's designed to accommodate virtually any sort of observatory, whether it's a roll-off observatory or a traditional dome-style observatory.
Again, this has been a fascinating look, I'm sure for our viewers, and certainly for me. I want to thank you, Rick, the CEO, and all of your other colleagues here at PlaneWave for allowing us to come in today and tour your facility and really get quite an education about how this is done.
Thank you very much, and we invite others who might be interested to come by as well. Thank you.
You're very welcome. This concludes this portion of the program. If you would like, you can go to our club website, the Ford Club. You can see the website address, I should say, down at the bottom of your screen. And coming up next is Stephen with What's Up in the Night Sky.
Thanks, Don. It's 2020 and we're going to try something brand new. What's up in the night sky for January 2020? The sun rises from 6:21 to 6:11 over the month and sets at 5:11 p.m. to 5:45 p.m. If you do the math, it turns out the days are longer. We just had the winter solstice just a few days before the start of the month. Astronomical night is from an hour and 40 minutes after sunset to an hour and 40 minutes before sunrise. Now, the moons. We have the first quarter on the 2nd. We have the full moon here on the 10th. We have the third quarter on the 17th. And we have this new moon, nothing here, that's on the 24th. Now, we're going to look at the superior conjunctions this month. We have the sun, and on the 10th we have Mercury lined up right with the sun. Superior conjunction, you won't be seeing Mercury really much of this month, much less on the 10th. We move on to the next slide. Also the sun, but it's on the 13th of January, and Pluto and Saturn are now right behind the sun, so we're not seeing either of those. Not that Pluto is easy to spot. And Jupiter is in both of these scenes. Jupiter is pretty close to the sun all month. And so all three of these are going to be difficult. Pluto, Saturn, and Jupiter are all in Sagittarius all month, and yet the sun goes from Capricornus to Aquarius. So Capricornus and Aquarius over here. So what's up? Why are the sun signs Capricornus and Aquarius when all of these objects are in fact in Sagittarius? And that's because tropical astrology really is based on the calendar, and we have the precession of the Earth's equinoxes, and it's a month out of date, really. If you really want realism, that would be sidereal astrology. Just note, I'm not terribly into astrology. The morning planets. Well, really, all we have is Mars. So here's Mars, and it's it's in the south. It rises at 4:51 in the morning, if you're awake that early, to 4:34 in the morning over the course of the month. It doesn't gain that much. Jupiter would gain 2 hours. It would get earlier by 2 hours. But we're on Earth, we're catching up to Mars as they both go around the sun. So it really is only half an hour that or not even a half an hour that we get. Note that we have Pallas over here, and we have Juno over here. These are minor planets. They're not hard to spot. I've seen Juno in binoculars, in very small binoculars at that. Any small telescope will show you these. You'll need a finder chart, and it should be a good one. And don't forget, it's cold at night, especially in the northern hemisphere. So then we have evening planets. We have Venus, Neptune, and Uranus. So Venus is right here by the horizon. It sets from 7:54 to 9:06 p.m. Neptune sets from 10:34 p.m. to 8:06 over the month. That's that 2 hours that I was talking about, more or less. And Uranus sets from 2:37 in the morning to just 39 minutes after midnight over the course of the month. So Venus in Capricornus moving to Aquarius, Neptune in Aquarius where it always is, and Uranus in Aries where you'd think that Mars is. And that is what's up in the night sky for January 2020. We don't charge for this show, but we may tax your brain.